Hi, this is Konstantin Kleinbeck. I'm with Technical University of Munich, and today I'm going to present hybrid foveated path tracing with peripheral Gaussians for immersive anatomy. In this work, we focus on visualizing anatomical data obtained from CT scans. Traditionally, such data is viewed as 2D slices, as can be seen on the left. 3D rendering approaches, like based on raycasting, improve the visual quality, with the highest quality achieved by path tracing approaches. These 2D slices offer the highest contrast and very fine detail and are thus the standard in clinical diagnostics. Path tracing, on the other hand, is more realistic, more intuitive, and thus well suited for education and planning. Together with the realistic rendering, this is also very suited for VR. However, we need to keep in mind that basically the nicer the approach looks, the higher the computational demand, and VR has very tight constraints, so we need some solutions here. Existing approaches look into how to speed up path tracing. Researchers have, for example, investigated temporal accumulation and adaptive reprojection, like reusing samples even though the head moves slightly in VR to denoise the volume for virtual reality. Adapting to the eye's anatomy and showing higher quality in the foveal region where the user is looking compared to the peripheral region of the vision. Utilizing the redundancies between both eyes to achieve better denoising in real time, or instead relying on pre-trained intermediate representations that are faster to render but lose interactivity on the way there. Our approach combines these methods. We use a simple pre-trained Gaussian splatting model for the peripheral vision and also stream high-quality path tracing rendering for the foveal region in. As soon as the user changes settings, we can regenerate the peripheral model and continue on. Now you might wonder, how can we do this in real time? Won't the Gaussian splatting model take too long to regenerate? And indeed, we can regenerate the peripheral model in under 1 second. We do this by training from very few images, 8 to 16 in our case, and crucially build upon a very high quality initial point cloud that we can extract directly from the CT scan. We do a very limited training run of 700 iterations and no densification at all. The path tracing views then are streamed in, it's color and depth images. We reproject them at depth onto the peripheral model, and at the same time we can reuse these images to refine the peripheral model so it improves over time value view. Our pipeline thus looks like this. We have 3 main components. One is the volumetric path tracing, the second one is the peripheral model training, and the third is the real-time viewer. Path tracing and peripheral model training usually run on some remote server, while the real-time viewer is local on the maybe standalone head-mounted display. These systems communicate through network socket messaging. Now during viewing, the system basically works in 2 phases. Initially, we need to create the peripheral model. For this, we take the medical volume that we want to view, render training images in a point cloud, train the peripheral model, and store it on the viewer. As we said, this works in under 1 second or around 1 second. And as soon as we have this volume, we can start with the interactive viewing, where we render views in response to head poses sent from the viewer, send back the post images in depth, and as we said, at the same time, we use these post images to refine the peripheral model and pass it on to the real-time viewer. Looking in detail at the real-time viewer, the pipeline looks as follows. We have the peripheral model that is shown. As soon as a frame comes in, we cut out the area of the peripheral model where the frame is, project the frame at depth onto the model, combine them, and achieve a combined view that has the highest quality in the foveal area where the user is looking, with lower quality provided by the Gaussian model in the peripheral vision. In this video, we can see how this looks like during actual usage. Here you can see me wearing a MetaQuest 3 headset and looking at a CT scan of a leg with the foveal area streamed in. Note that the Quest doesn't have any eye tracking, and our system thus works with fixed foveated rendering, so the foveal area is just in the middle. It's pretty hard to see on this video where the foveated area is, thus we lower the visibility of the Gaussians. This is not done during normal usage, but in this case just for the video to see where the view is that we stream in. And we can see that it very neatly fits onto the Gaussian splatting model, and with the depth reprojection fits in nicely. Looking at the performance of the initial model creation, we have evaluated different options in terms of views that we need for the model and the sample size for each. Let's focus on one parameter set that we found got very nice results. In this option we use 12 views with 8 samples each, and in this graph we can see that the training time to render these 12 images takes around 150 milliseconds. Then we start the training and we can see that early peripheral model is done at around 300 iterations, around 500 milliseconds. We already have something that we could stream to the headset if we wanted to, and the peripheral model training is finished at 700 iterations at around 1 second. On the right you can see that the quality is very close to the actual ground truth already. Looking at the performance during viewing, we can see that our approach achieves quite similar performance in the peripheral region compared to just path tracing or just 3D Gaussian splatting. It depends a little on which measure you look at. At PSNR we are slightly lower, on LPS we are slightly better. Then we can also see on the rightmost column that our approach, after continuous refinement with additional views captured during viewing, our approach gets a lot better. So there is definitely a positive impact on reusing these views and training while the user looks at the anatomy. Looking at the foveated region specifically, we can see that we outperform both path tracing and just Gaussian splatting on all metrics, and we can also notice that our system is more robust than just both of these two options. We achieve better, more robust, more continuous quality than these two. In conclusion, we can present limitations and benefits. We split these up into areas: limitations of the approach itself and limitations of this implementation of the approach. The approach itself obviously increases the complexity by combining multiple elements together. It is best suited for limited scenes with slow movement, where the area that we want to reconstruct is small, and we need the ability to create this initial point cloud at good quality really quickly. This is easy for CT scans, but for other data it might be harder. And limitations specific to this work that also inform future work that could build upon this are that we have untested and unoptimized interconnections. There's definitely some quality that we can in there. The performance numbers that we report are the systems itself without taking the interconnections into consideration. The continual refinement approach is just approximated right now. There's with manual copying of files, and it is not tested with users yet. So while this looks nice in our preliminary testing, there's no user info yet how nice users think this works. The benefits on the other end include this is improved quality and speed over the state of the art. We achieve interactive and robust against latency and lag visualization. This robustness against latency and lag also lets us trade rendering speed and quality for each other. So we could say we want to render with more samples and then reproject an image in fewer times but with better quality. And crucially, our approach benefits from both improvements to path tracing as well as Gaussian splatting, because we integrate both of these techniques. So if either one gets better with new research, this approach also improves. Thank you for your attention. This was hybrid full-weighted path tracing with peripheral Gaussians for immersive anatomy. If you have any questions, feel free to reach out to my email. Thank you.